In this lecture, we will be studying curves in three-dimensional space and vector-valued functions. Let's start with our definition of a parametric curve. A parametric curve C in R3 is a triplet of functions, x equals f of t, y equals g of t, and z equals h of t, that give x, y, and z as continuous functions of the parameter t in some domain I. The x equals f of t, y equals g of t, and z equals h of t are called parametric equations. And the natural thing to think here is that if you consider your parameter time, we can think of that triplet, f of t, g of t, h of t, as the location of a particle moving in three-dimensional space. So we have some trajectory of a particle moving, and at time t, we're getting the coordinates with that x equals f of t, y equals g of t, and z equals h of t. So at any time t, this triplet tells us where this particle is, and the trajectory of the particle is tracing out a curve in three-dimensional space. We also add the terminology of the idea of a position vector. So the position vector for the parametric curve C is the vector with variable t, defined by this expression here, where each entry comes from the respective parametric equations. And this is a vector-valued function. A vector-valued function, as we wrote here, on a domain D, is a rule that assigns a vector in space to each element in D. So t is our parameter. T lives in that domain, and for each t, we get a vector on the right here, as given by these parametric equations. And we can think of this position vector as pointing to our particle that is moving in space. So if this is our r of t, this point in space here is the point f of t, g of t, h of t. And our vector, our position vector, is always pointing to it. Hence the name position vector. It tells us, if we have the vector begin at the origin, the end of the vector tells us where the particle is. So you could imagine, as this particle is moving around, if we go back to our picture of our parametric curve that's being traced out, which we called C, as you run the clock, that particle is moving along this curve, and r of t is tracking it. Its base is at the origin, and the tip is always pointing right to the point moving through space. Now that we have the idea of a vector-valued function, we need to bring in some of our calculus concepts to this. And the first concept is, of course, the central concept that underlies all of calculus is the concept of the limit. So we say the vector-valued function r of t equals f of t, g of t, h of t with domain D has limit L. So this is a vector of three constants as t approaches t naught, and we denote it in the usual calculus style. The limit as t goes to t naught of r of t equals L if, for every epsilon greater than 0, there exists a number delta greater than 0, such that for all t in the domain, the magnitude of the difference between the vector r of t and the limit vector L, so think of this as the Euclidean distance between these two vectors, is smaller than epsilon whenever the absolute value of t minus t naught is smaller than delta. Intuitively, this is saying Epsilon is an error tolerance. You're given that error tolerance. If you want to get your position vector for your particle within that error tolerance of epsilon, you just have to pick times that are close enough to time naught, t naught. And that measure of closeness is this delta. If you shrink epsilon, you will shrink your delta. But you can always find a delta such that if you pick times close enough to time t, you can get the distance between L and R of t to be smaller than that error tolerance epsilon. Let's depict this and try and get an understanding of what's going on visually. So let's consider again this vector-valued function to be the position vector of our space curve C. And suppose we're here at time t naught. So at t naught, this is where our particle is. And we want to show visually what it means to have the limit L. Now the limit L has an x-coordinate of L1, a y-coordinate of L2, and a z-coordinate of L3. For the limit of r of t to be equal to L, and remember the idea is r of t points to this point here at time t naught. If we're given an error tolerance epsilon greater than 0, what we want is the distance between the point r of t and the point L to be smaller than epsilon. Well, what does that mean? Think of this as points. The distance between 2 points is smaller than epsilon. That means that if we put a sphere of radius epsilon around this point, we want r of t to be inside of that sphere. We want the point to be inside of that sphere. And this is telling us that this limit of, as t goes to t naught of r of t equals L if for every epsilon greater than 0, so for every sphere that you can put around this point L, we need only choose t minus t naught in absolute value to be smaller than delta. And so t minus t naught being smaller than delta is going to translate to a set of times that keep the curve within that sphere. So as long as we choose, there's some delta that depends on epsilon, and as long as we choose times t to be within delta of time t naught, you can see this lavender piece of the curve is within this orange sphere. And the key thing to recognize is we said this works for every epsilon greater than 0. So if you shrink epsilon, think about halving epsilon over and over. Halve the radius of this sphere. Well, you just have to reduce the arc length, the length of this lavender curve, which means you shrink delta. Okay, cut the radius in half again. You shrink delta. And as long as you always have this picture, then by definition, the limit as t goes to t naught of rt equals L. So this is the idea of the definition of a limit for a vector-valued function, and you can really think of it as an extension of the definition of limit that we learn in single-variable calculus when we really start studying calculus for the first time. The next calculus concept we need to think about is that of continuity. So the vector-valued function the same one we were looking at, r of t equals f of t, g of t, h of t, with domain D is continuous at the point t equals t naught in the domain of D if the limit as t goes to t naught of r of t equals r of t naught. Further, we say the function is continuous if it's continuous at every point in its domain. So let's come back to the picture, and we see that this again is an extension of our understanding of the concept of continuity from single variable calculus, where if we are again at a point at time t naught, then the function is going to be continuous if the limit from the left and the limit from the right match. So the limit, first of all, has to exist, and the limit has to equal r of t naught. This translates into the idea of no hole and no jump at this point here at time t naught. Let's look at an example. So consider this vector valued function, cosine of t, sine of t, t. And we're going to think of this as a position vector for a particle moving through space. And let's think about it for t non-negative. Now, one thing that we'll note first is that when t equals 0, we have r of 0 being cosine of 0, sine of 0, and 0. We know cosine of 0 is 1, sine of 0 is 0. So we have the vector 1, 0, 0. And with our labeling, let's imagine here that our 10 is 1. So this will be 1, 1, minus 1, and minus 1. So we know that we're going to start here at this point at time 0. So that's where our particle will begin. But before we continue to try graphing other points, let's note something about this. The x-coordinate is cosine of t, and the y-coordinate is sine of t. So note that if we square those, so if we take x of t and square it, and to that we add y of t squared, that's cosine squared t plus sine squared t, which we know is 1. This means that no matter what the value of the parameter t, if we think of it as time, no matter what time it is, the x-coordinate squared plus the y-coordinate squared equals 1. Now in 3 dimensions, x squared plus y squared equals 1 is a right circular cylinder. Specifically, it's that right circular cylinder. So when we say right circular cylinder, think like a can. And projecting down into the xy plane, the shadow of the particle, if there were a light shining directly from above, would be moving around on the unit circle in the xy plane. So what will happen, and let's get a sense of where this would be at a later time. Let's think about another natural time. How about instead of x being 1, what do we need for y to be 1? Well, that would be the time pi over 2. So at time pi over 2, we have cosine pi over 2, sine pi over 2, and pi over 2. Cosine of pi over 2 is 0. Sine of pi over 2 is 1. So we're at the point 0, 1, pi over 2. So we were here at time 0, and now we're at time 1. The x-coordinate is 0, the y-coordinate is 1, but now the z-coordinate is no longer 0, it's pi over 2. So we are now above the xy plane. So we would be, say, here, at a height of z equals pi over 2 above the xy plane. If we go to t equals pi, r of pi is cosine of pi, sine of pi, and pi. Cosine of pi is -1, sine of pi is 0. So now the x value is -1, the y value is 0, but our height is higher, twice as high as it was at this previous point. So we are now at this height of pi. And so what's happening is this is moving above the unit circle in this counterclockwise fashion, but as it moves, it's getting higher and higher. And so what we actually have is a helix. And so this is a classical example in terms of parametric curves, better depicted here. And so we see the axes. Here's our x-axis, here's our y-axis. So here y is 0 and x is 1. And we can see we're spinning around in this helix fashion. Using MATLAB, we can see it a little bit better, where we can actually move it around. So we see, rotating it, how this helix actually works. And notice, if we take a bird's eye view, so we're going to look at this straight from above, you'll notice when we're just looking at the xy plane that it collapses into that circle. And so this would be that projection of the projectile as it moves in a helix into the xy plane, and so that would be its shadow in the xy plane, the unit circle. But this is what our helix looks like when we tinker around with it in 3 dimensions. Let's consider another example, r of t equals t cosine of t, which we already have graphed here. And this is a slithery path, the kind of path that the American sidewinder rattlesnake would make in the sand. And we can understand how this is working. Think about these x and z coordinates. So as time increases, we start here at time 0. And as we run the clock, both the x and the z coordinate are increasing at the rate of t. And so the x coordinate is moving to the right, the z coordinate has us moving up, but this y coordinate you see here is oscillating between -1 and 1. And so that's what results in this slither path. Now that we understand what position vectors and curves in space look like, we have to look a little bit more into calculus terminology and calculus ideas, such as derivatives, and we'll explore those in the next lecture.